All right, it's time to talk periodic table trends. Are you ready? All right, so here's the arrangement of the periodic table, the modern periodic table. And if you recall, it is arranged by atomic number. And when you arrange it by atomic number, we are going to have repeating patterns based on the number of valence electrons. And the number of valence electrons, remember, determines properties, how elements react. And that is why we see those repetition of properties. So periodic trends. Well, a trend, you should know, is a predictable change in a particular direction. So tends to increase, tends to decrease, tends to stay the same, a trend. And the arrangement of the periodic table reveals trends in the properties of these elements. And we're going to talk about a few of these trends. Okay, so what affects trends as you go across a period? So here's an example seeing period 3. What affects trends going across a period? Well, more protons and electrons are added as you go across a period. So you can see sodium has 11 protons and then 11 electrons as an atom. Magnesium has 12, aluminum has 13, silicon has 14. But the nuclear charge is increasing. So that means this is having more and more protons added to it. But they're being added to the same energy level. So you can see sodium has 1 electron in the third energy level, magnesium has 2, aluminum has 3, silicon has 4, and so on. So because of that, the electrons are more attracted. So they get pulled in tighter because the nucleus is increasing in charge, but the electrons are being added to the same energy level. So we are able to pull the electrons more tightly. And the properties that we see going across a period are a result of that. Now, what affects the trends that we see going down a group? So you can see we have 2 groups here, groups 1 and 2. Well, the number of energy levels increases as you go down a group. So you can see beryllium has 2, magnesium has 3, calcium has 4, strontium has 5, barium has 6, and so on, okay? Now, this reduces the attraction for the outermost valence electrons. So here we have the atom getting bigger and bigger and bigger, so it's not able to pull those valence electrons as tightly. So the electrons are less strongly attracted. Now remember, we're talking about valence electrons, the ones on the outside. So when we compare valence electrons that were in energy level number 2, we could pull them pretty tight. But in energy level 3, a little less tight. 4, less tightly. 5, less tightly, and so on. So the first one is ionization energy. So you don't need to memorize these values. So if you look at table S, one of the columns says first ionization energy. Well, let's talk about what ionization energy is first, so then you can see what that means to use that qualifier first. Well, ionization energy is the energy required to remove an electron from an atom or ion. So here's the atom with its electrons and its energy needed to pull one of those electrons away. And because it says first ionization energy, it's the energy required to pull away the first electron. There would be other values for second ionization energy and so on, but we are only going to focus on this one, the energy needed to pull away that first electron. You don't have to guess on the numbers. You can look them up on table S. Understanding the trends helps. You don't have to look every single thing up. But again, this is not a memorized thing, but through practice, you should be able to retain it. So first ionization energy. All right, first ionization energy. It is the energy required to remove an electron from an atom. Pull it away. Now remember our trends. As we go this way across a period, right, we have more protons added to the nucleus and the electrons are added to the same energy level. So we're pulling them tighter. They're held more strongly. And as we go this way down a group, we add more and more energy levels. So the atom gets bigger and is less able to pull those valence electrons as tightly. Okay, so if we look at our trends then, as we go across a period, what happens to our first ionization energy? It increases, right? So the first ionization energy increases going this way. what happens to the first ionization energy as we go down a group? It decreases. So that's the way you need to know the trends, going down a group and across a period. Okay. All right, so as you go down a group, what happens to ionization energy? It decreases. As you go across a period, what happens to ionization energy? It increases. All right, so let's talk atomic radius. Okay, now since atoms are so small, it's relatively hard to measure the radius of an individual atom. So we do it kind of in a different way. We take the radius of two bonded atoms. So we take the measurement from the nucleus of one atom to the nucleus of the next atom when they're bonded, and then we have that distance to get the atomic radius. So kind of a weird way we get it, but anyway, the values are still on table S. And it is a little bit hard to determine, so we use the bond radius. But again, you don't have to guess for these values. They are on table S, but it does help to have a kind of an idea in your head so that you have less to look up. Because if you have to look up everything, sometimes you run out of time. So again, look at table S for the values, and let's look at the trends. Okay, atomic radius, the size of the atom. Okay, here you see again the values for going across a period, period 2, and then you see the values going down a group for period 2. So what happens to atomic radius as you go across a group? You should see that it decreases, right? And what happens to atomic radius as you go down a group? It increases. So you can see you don't have to memorize these. Look them up. Okay, don't stress yourself out. Look them up. So as you go down a group, what happens to atomic radius? It increases. As you go across a period, what happens to atomic radius? It decreases. Okay. All right, ionic radius versus atomic radius. This is asked a lot. So here we have atoms. Okay, the relative size of the atoms. Now, when sodium becomes an ion, notice it becomes a cation, a positive ion. So that means it loses an electron. What happens to its size? Gets smaller. And then look at chlorine. Here's chlorine as an atom. When it gains an electron, it becomes an anion. It has a negative charge. So what happens to its size when it gains an electron? It gets bigger. So if an atom loses an electron, its ion is smaller. And if an atom gains an electron, its ion is larger. But what is losing or gaining the electron when I'm talking about that? The atom, okay? Here is just another quick reference. You can see all of the atoms are in gray and the ions are in blue. So you can see when we have things that form positive ions, the ions are smaller. And when we have things that form negative ions, the ions are larger. All right, so now let's talk electronegativity. So we have another value on the table S. Electronegativity is the measure of the ability of an atom when it's bonded to attract an electron. So it's like kind of thinking about it like the opposite of ionization energy. So again, you don't have to guess. The values are found in table S. It does help if you have an idea and if you do remember some of it, but again, you don't have to focus on memorizing values for sure, but trends, it's good to have an idea. All right, let's look at electronegativity. Again, look at these values. This is period 2. This is group 2. So what do you see happening, right? As you go across a period, the electronegativity goes up. As you go down a group, the electronegativity goes down. So what is electronegativity? Remember, that is how strongly an atom will pull an electron in a bond, okay? So as you go down a group, electronegativity what? Decreases. As you go across a period, electronegativity what? Increases. Okay, fluorine being the most electronegative element, you see it 4.0. I always think about perfect score, 4.0. And then cesium, you can see in this section right here, it has the lowest. So we're going to have the highest up here with fluorine and the lowest in group 1. All right, now what about metallic character? So metallic character versus non-metallic character. So metallic character is how metallic an element is. So remember, metals lose electrons, okay? So they give up their electrons. So that means it would be easy to pull an electron away. So that means we'd need a low ionization energy. And where we have a low ionization energy is in group 1 at the bottom near where francium is. So that would be the most metallic, okay? So as you go down a group, what's happening to the metallic character? It is increasing, more metallic, easier to pull an electron away. Okay, what about non-metallic character? Well, so if metallic character is ability for something to lose an electron, to pull it away, for non-metallic character, we're talking about the ability to attract an electron. And that would mean have a high electronegativity, right? The ability to attract an electron. So where do we have elements that have high electronegativities? Remember fluorine, that 4.0, the perfect electronegativity, that is at the very top of group 17. So as you go across a period, non-metallic character is increasing. So metallic character increases as you go down a group, and non-metallic character increases as you go across a period. So the most non-metallic would be fluorine, and the most metallic, francium. So they're both Fs, they're just on different ends. Okay, now let's look at melting and boiling points. So again, these values are on table S. Notice that we use Kelvin, and again, we use Kelvin so we don't have to worry about negatives. It's real simple conversion from Celsius to Kelvin. You just add 273. Melting, remember, is going from a solid to a liquid, so it's at that temperature. So if you heat up something to the melting point, the transition is going to begin from solid to liquid, and it will remain at that temperature until that change is complete. Boiling is going from a liquid to a gas, so if you continue to heat it, and you get to the boiling point temperature, it is going to begin to change from a liquid to a gas. Keep it at that temperature. It's going to stay there until all of it changes from a liquid to a gas. So again, you don't have to guess for these values. They can be found in table S. It's just not as neat as some of the other trends we just talked about. So you can see these are based on the 4th, the 5th, and the 6th periods. And you can see that what happens is the melting points and boiling points, so it would follow a similar trend, go up and then down, and then there's another little kind of burst up and down, okay? But in general, it is not just increase or just flat decrease. But again, this would just be a matter of checking on table S. So the trends is a big increase, big decrease, and then just a little bump, okay? But you can see both the 4th and the 5th, and then also the 6th period follow that same trend.